Good morning, this is Sarah Parker, and I'm doing our presentation for Assignment 5 for Machine Learning. This presentation asked us to take a generative adversarial network that was originally in an MLP and convert it into a CNN style architecture. And the reason that we did this is because the data set that we're using is the MNIST data set, which is tens of thousands of handwritten images. And so the CNN works better with spatial recognition and pixels versus that MLP. Essentially what the GAN is going to do is we create a discriminative and a generative model. And our generative model is going to produce fake images that are similar to the data set. And the discriminator is going to determine whether that's a real image or a synthetic image that we generated. And as the model progresses, the discriminator should get better at figuring out whether the image is fake or real. And that makes the generative model work harder to produce better images. So the big thing was changing the CNN to the MLP, the MLP to the CNN. And so for our generator architecture, we're going to map a 100-dimensional noise vector to a 28 by 28 image. The architecture that we used was linear 100 to 128 by 7 by 7 ReLU, which projects our noise into the spatial feature map. And then we're going to reshape that using view and forward. We're going to upsample it twice using a convolutional 2D. So 128 to 64 with a K of 3 and a padding of 1. Batch normal 2D and ReLU to put it into 14 by 14. Upsample it again 2 times, so taking our 14 by 14 and putting it into 28 by 28 by doing a convolutional 2D 64 to 1, all that's the same with a ton. So we get our 28 by 28. The padding of 1 on a 3 by 3 convolution keeps our spatial stays the same size after the convolution. The upsample does all the spatial growth. So that's our model for the generator. And our discriminator is going to take that image that we just produced, that 28 by 28, and it's going to output a real fake probability. So it's going to do the 2D 1 to a 32 with a leaky ReLU plus a dropout to drop it back down to the 14 by 14. And then we're going to convolutional 2D it again with a batch norm 2D leaky ReLU dropout to take that from the 14 by 14 to the 7 by 7. Then we're going to flatten that into a linear 64 by 7 by 7 to a 1, adding a sigmoid. So essentially, we're going to get a 0 or a 1, a 0 to a 1 for our probability to figure out whether that's likely to be fake or likely to be real. This is the data set that we used. It's the MNIST. And you can see that it downloaded here appropriately. 60,000 images. We added our optimizers and our loss. We used a cross entropy for our loss. And then we're going to compute our discriminator accuracy, and we print the progress after every epoch, and then I logged that to a CSV. And then I saved images every 800 epochs so that we could see the progression of how our model was doing. So this is just the output of the epochs and the loss and the accuracy, but all that's saved to a CSV. So I'm going to jump over here to our report so that we can go over it. This is just going through the configuration and the hyperparameters that we use, that binary cross entropy with the atom optimizer for the generator and the discriminator. The real label for valid was 1, fake label for 0 was fake. So here is what we have discovered. So this is our training loss. The orange is the generator loss, and the blue is the discriminator loss. So the discriminator, as you can see, stabilized pretty quickly around that 0.5 to 0.6 mark, and it stayed pretty flat throughout training. So it was consistently learning to distinguish the real from the fake. The generator loss, however, you can see increased over time, reaching a mean of like 1.07, but it actually peaked right here around 2.37. And this shows that our discriminator became really capable of detecting those generated images. and it was making the discriminator could detect the images, but it was making the generator work harder to produce those images, though it still did. The images continued to improve across all 10,000 epochs. So our discriminator accuracy over here is actually pretty high. Ideally, you want that closer to like 50%, and ours is averaging around 71.9. This kind of told us that the discriminator maintained a moderate advantage over our generator. But like I said, our generator actually still showed really good image progression as we went along. So I picked a couple of images just to show what it looked like for our model. This was 0. So at 0, it was just doing the upsampling. So, but you could still see like it's noise, but there's definitely black and white color variations here. But even by epoch 3200, the numbers are starting to look pretty good. They're definitely more kind of blurry and not as clean around the edges, but you can see some that look like a 9, some that look like an 8. Maybe this was supposed to be a 7. We have a 0, so it's looking good. And then by 5,000, it's definitely cleaner. You get less noise. The edges are smoothing out and they're cleaner. You get a couple other numbers, maybe a 3 and 6. 7,200, I feel like looks pretty similar to 5,600. It might even look a little bit blurrier to me. But by 9,000, we're looking great. So we've got 0s, 7s, 5s, 9s, 6s, 3s, 1s. Our generator did a really good job of making like the crisp background black and our images white on the foreground. And it was much cleaner. This looked much better than the MLP architecture that we were given as a baseline to compare those images to. And that's just because, like I said, that CNN is better at that spatial texture compared to that MLP. One thing that it was a difficulty for me at first, when I first ran it, the images looked okay, but they actually didn't look that much better than the MLP to me. They were still really grainy. They were kind of disfigured, and it was really a bunch of linear strokes. It looked like a bunch of 1s and maybe some 0s. And so I was like, something's not right. This is supposed to look better. It's not supposed to look worse. So we figured out there were a few things wrong. The data tensor was still shaped as an N784 rather than our 28 by 28. So our convolutional 2D layers were receiving an incorrectly formatted input. So it was just shrinking unexpectedly after our convolution. So everything was distorted. Originally, there was no dropout in the discriminator, and that allowed it to overpower the generator before anything meaningful could occur. So once we corrected these 3, that gave us the images up above, and I felt like that was much closer to what the assignment was asking us to do. So that was essentially the assignment. So this was fun. I love the concept of an adversarial network and 2 competing models, because you're making them both work against each other, but also trying to make them each work their best. So that was a really fun assignment, but that was taking our MLP architecture on a GAD and turning it into a CNN architecture. Thank you.